What do Tinder, Netflix, and Spotify have in common? They all rely on the same mathematical tool to create matchings and recommendations, the dot product. In my linear algebra course, I like to pose the following problem to my students to teach them about dot products. Say I want to match up students to form study groups or study partners. I want to ensure these groups get along and are productive, so I make everyone take a survey about their interests and habits, where for each question, they choose where they fall on a 5-point scale between two options. For example, are they more of a night owl or a morning glory? Do they prefer camping or a resort? Then I convert the 5-point scale, so a -2 represents strong preference for the first option and 2 represents strong preference for the second, and 0 means equal preference for both. Now the question is, once I have all this data, how do I determine how to match everyone up? This is the same type of question that matchmaking services like Tinder and Hinge ask as well, or recommendations given to you on Spotify or Netflix. By the end of this video, we'll see how dot products and vectors help with creating matching algorithms and learn just how versatile the dot product is. Welcome back to our course on linear algebra, the math of packets of numbers. For example, those represented by vectors and matrices. If you haven't seen our first video in the series, you can check it out with the link in the description or by clicking right here. Okay, back to our study group matching question. Here are survey responses from 4 students. Each row shows the responses for a student, and the columns represent answers on the same question. Take a moment and look at the table. Which student would be the best match for student A? And which one would be the worst? Could you rank the students from best to worst? Or could you create a match score to tell how well each student fits with student A? Pause the video here and think about those for a few minutes, and go ahead and drop your thoughts in the comments below. Did you come up with a ranking? Let me guess what you did. You compared A's answers to other students' responses for the same questions, tracking who had similar or different answers. What you didn't do was compare A's response to one question with B's response to a completely different question, because without more context or data, that just doesn't make sense. Most of my students will rank student D as the best, C in the middle, and B as the worst, because D has a lot of exact matches or responses that are at least the same sign, while B has a lot of responses that are the opposite sign of A's, and student C has a mix. What about coming up with a match score? How would you calculate a score for B, C, and D that's a measure of how well they match with A? If you haven't tried this yet, pause and think about it for a few minutes. Most of my students do this calculation. Pair up answers with A, take the difference, and add up all the differences to get a total. My students argue that a small value, close to 0, is a good match. A score of 0 is a perfect match, since that would mean all the answers were exactly the same. And a large value would be a poor match. Other students instead suggest multiplying paired answers and summing the results. The logic being same-signed pairs contribute positively to the total, while opposite-signed pairs subtract from it. And a positive sum indicates a stronger match, with higher totals being better and negative totals worse. Using this method, we get the same ranking as before. The only difference between the two approaches is the operation to calculate the amount of a match for each pair. Actually, this multiplication method is exactly what the dot product is. We take 2 vectors with corresponding values in each row, multiply them together, and then add them all up. This operation is so useful and widely used, it even has its own notation, a large dot. Both the difference and dot product methods could be used as a measure of similarity, but the dot product method is more useful because it is related to many ideas of similarity. So what do we mean when we say 2 vectors are similar? Or what ways can we think about similarity between vectors? Here's an image to help us think about similarity of vectors. Which of these vectors would you pick as good matches to vector A? Which ones would be bad matches, and why? Pause and think about that for a minute. Which ones are most similar to A? My students often come up with 4 different justifications. First, the 2 most common answers from my students are V and E. Students argue V because the angle between V and A is smaller than A to other vectors. Others argue E because the heads of the vectors are the closest in distance. A few students will suggest T. Even though there is a strong argument to say that this is the least similar vector, it does lie on the same line as vector A. So they have something fundamental in common. We'll explore what that is at the end of this video. And lastly, I also have students argue that R is the closest. This argument involves a new concept called projections, and we'll cover this in depth in a follow-up video later. But in short, a projection is found by dropping perpendiculars from the head of one vector onto another vector. Notice as we project all of these vectors onto A, the projection of R hits the head of A exactly. Okay, so my students see 4 different ways 2 vectors could be similar. Each one of these are connected to the dot product match score. However, the difference operation score is only connected to one of these. This is one reason why mathematicians prefer the dot product match score, but we will find other reasons too. So which of these similarities does the dot product correspond to? Well, none of them exactly, but we use it to calculate the match score for all of these, and I'll show you how. Suppose we want to calculate the distance between the head of A and the heads of the other vectors. We can do that with the distance formula, which is just an application of the Pythagorean theorem, like this. But notice, squaring the lengths in each direction can be done as a dot product. So we can write down a formula for the distance between the heads of any 2 vectors, u and v, with the dot product. Because the length of a vector and the distance between heads of vectors are so useful, mathematicians developed a notation that means the length of a vector. It's a double absolute value sign. It's the absolute value as the distance a real number is from 0. The double absolute value sign is the distance or length of the vector from head to tail. What about measuring angles with dot products? Well, one easy angle to measure is 90 degrees. The dot product of 2 perpendicular vectors turns out to always be 0. Try it yourself. Draw a vector, then create a perpendicular one by swapping the x and y coordinates and changing one sign. Their dot product will always be 0, no matter the values or scaling of the vectors. This makes some sense because perpendicular vectors are going in unrelated directions, so no amount of movement of one vector goes in the direction of the other. Many of you probably picked vector c to be the vector least similar to vector a because they're perpendicular to each other. So the amount they have in common is 0. Okay, what about all these other infinitely many angles? Can we calculate angles between vectors using a dot product? Yes, we can. We can try to calculate the angle using some trigonometry. We give a brief overview here, but we'll develop that formula in detail in a subsequent video. We start by dropping a perpendicular vector from the head of one vector onto the other vector. Finding some lengths and using the adjacent side and hypotenuse, we calculate the cosine of the angle, resulting in this formula, and if we solve for theta, we get a formula for calculating the angle between 2 vectors. Notice, a main operation that we do in the formula is a dot product of the 2 vectors. But we can also use the dot product to calculate the lengths of these vectors as described earlier. If we think that small angles are a good measure of similarity for these student preference vectors, then we can use this formula and calculate the values in degrees from 0 to 180. But if we don't care about the angle itself, we can use the cosine of the angle, and that involves less computation. The cosine of the angle has a really nice scale, 1 to a -1, with 0 being perpendicular. When we use the cosine of an angle to rank matches, it's called the cosine ranking method. Now let's apply the cosine ranking method to our student survey data from the beginning to see how well students in my class match with each other. Here are the survey results of 101 of my former students. I've added 2 fake students to compare them to, midnight and noon. These 2 are exact opposites of each other with their responses. Let's first calculate their individual products with midnight in the spreadsheet, and now let's sum them up. That will give us the dot product of each student with midnight, which is the top portion of our new cosine ranking formula. Now for the bottom portion, we need to calculate the length of each vector, the vector for midnight and the vector for each individual student. This is an easy one, because the length of a vector is just the square root of the dot product with itself. Now we can put this all together in this column to find the cosine of the angle measure between the vector for midnight compared to each of the other students below. Sorting by the cosine to rank the students puts the best matches at the top. We can see that there is one student with the exact same answers as midnight, and many others with values close to 1. Notice how all values are between a -1 and 1, as we would expect, where +1 indicates a perfect match here, and -1 indicates an exact opposite. This would be akin to our t-vector from the earlier example. They do share a similarity. The absolute value of corresponding entries is the same, but the signs are exact opposite, resulting in vectors that lie on the same line, but move in opposite directions. Our final question is, how do dot products relate to projections, and we'll hit that in a later video dedicated to projections. So a dot product is some measure of similarity between vectors, and we saw how it's related to 3 of the 4 ideas my students thought of as similar. We did the cosine ranking method on my students to show how we can use dot products to solve a matching up problem. Some of you may be wondering about the cosine ranking and correlation. Both of them show a similarity, but they approach it from a different perspective. Correlation is usually presented with how tight data is around a best-fitting line. That view is of multiple points in a 2D plane, or multiple 2D vectors. But we can view the data as 2 vectors in a higher dimensional space. The angle between them, as we saw, is used for a measure of similarity. Correlation and cosine ranking are exactly the same if we subtract the respective means from the vectors before calculating the cosine. But I want to point out that the math is simpler to reason through with 2 vectors, and it's easier to see the similarity geometrically as 2 long vectors rather than many dots around a line. Since dot products are related to distance, angles, lengths, and dropping perpendiculars, you can imagine that dot products are powerful tools for real-world coordinate geometry. We will find out in a few more videos how other tools in linear algebra create powerful applied geometry tools, which is why they are used so much in computer imaging, graphics, or movements of drones and robotic arms. Well, now you can start your own dating app, since you now know how to match up people that have similar interests. But if you do, you owe me half your profits. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.